Good afternoon, everyone. My name is Rupa Rani, and today we will discuss the topic B3 in data structure, in data analysis, and design analysis of algorithm. Start with topic B3. First of all, what is B3 in DA? B3 is a balanced search tree which is designed to work well with the magnetic disks or storage devices. As I told you in the points, in a B3 of order m, each node can have up to m children and m-1 keys, which allow it to efficiently manage large dataset. Means, in earlier days, we listened the music through the cassettes. There we use the concept of B3. That's why I told you that B3 is a balanced search tree which is designed to work well with storage devices or magnetic disks. Now, according to the first point, we will see, suppose we have an example and we have a key value like P. This is a pointer and this one is left child and this one is right child. This pointer will store the address of this left child and this pointer will store the address of this right child. According to this statement, in a B3 of order m, each node can have up to m children. These are the children. Suppose m equal to 2. According to this statement, it can have up to m children and m-1 key. Here we can see only one key. It means 2 minus 1 equal to 1 key. This is the meaning of this statement. Means, suppose we have a single key, then there will be 2 children. If there are mandatorily 2 children, it means there will be exactly 1 key. Like this. Because this left one pointer will store the address of this left child and this right one pointer will store the address of this right child. In the second point, one of the standout features of B3 is its ability to store a significant number of keys within a single node. Means we can have handful to 1000 key values in B3. In the third point, it significantly reduces the tree's height and hence we can reduce the costly disk operations. In the fourth point, B3 allow fast data retrieval and updates, which make it an ideal choice for the system requiring efficient and scalable data management. Suppose we have a large size of data, then it will be easy to manage that data in an efficient way. And last point, by maintaining a balanced structure at all times, B3 deliver consistent and efficient performance for the critical operations. Like in B3, we have basically 3 operations: search, insertion and deletions. We will study these operations in the further slides. This is all about the introduction part of B3. Now, see the properties of B3. First property, all leaf nodes of a B3 are at the same level. Means they have the same depth. Means height of tree is the same. I am taking one example. Suppose we have 2 key values B and M. And this will be a pointer and this one. There are 3 children. If we have 3 children, like in previous slide, I told you, if order m is equal to 3, then there will be m-1 key values. Means children's are 3, then m-1 key value, 3 minus 1, 2 key values. And depth of all these leaf nodes are same. because these all are at the same level. Now, in the next property, the key of each node of a B tree should be stored in the ascending order. As in this example, suppose we have two key values B and M. There is a left child on the left hand side of B. It means the value which we store on the left hand side, it will be less than B. These are the alphabetic values. So we can have only A in the left child. After this B, the value must be greater than B and less than M. So we can have value here greater than B and less than M. We can have D, E, F, G like this. At the right side, we can have an alphabet which must be greater than M or equal to M. So we can have here N, O, P, Q and so on. This is just an example. So we can have any value greater than M on the right side of M. So you can see these all are in the ascending order. It means suppose we have more than one alphabet in this, then all must be in the ascending order. If we are taking digit, then that must be in the ascending order. If we are taking alphabet, it also must be in an ascending order. This is the property, one of the property. In the third property, in a B tree, all non-leaf node should have at least M by 2 children. Third property and fourth property we will understand in the next slide with one example. Fourth property says all nodes should have at least M by 2 minus 1 keys. Here you can see M. What is this M? M is the maximum number of children possible. In a B tree. What is M? M is the maximum number of children possible. Like these are the maximum number of children, 3. So key value is M minus 1, 3 minus 1, 2. Right? Next, fifth one is if root node is a leaf node. Suppose this is a root node and this is a leaf node, means there is no other node. It's a single node. Then it will have no children and will have at least one key. It means there will be no left child and there will be no right child. This one is only a single key. Right? If root node is a non-leaf node, then it will have at least 2 children and at least one key. Suppose this B is a non-leaf node. Non-leaf node means this is not a single node. Means it can have more than one node. Then there will be at least 2 children. Right? We have a single key only on the left hand side. We will have left child, on the right hand side we will have right child. Means this is saying it will have at least 2 children. At least 2 children it will have and at least one key. This is the one key. At least 2 children means the lower bound is equal to 2. Right? We will see this in the further slide. That's why I told you we call it lower bound. Means minimum children we can have 2. 1 and 2. And the last property is a non-leaf node with n minus 1 key values should have n known null children. All these property we will understand in further 2 slides. After seeing those 2 slides, you will better understand the order and degree both, and lower value and upper value, lower bound and upper bound as well. Now, Suppose we have a numerical problem. Problem is given to you and M order is mentioned in that problem. In any numerical problem of B3, either order is given or degree is given. Suppose order is given in the numerical problem, then how will you solve it? Just see this. Order is given. In that case, you have to find the maximum number of keys and minimum number of keys. For that problem. Now we will see the maximum number of keys. Suppose M equal to 3. Then what is the maximum number of keys? M minus 1. It means 3 minus 1, 2. Right? And what are the minimum number of keys if order is given? Minimum number of keys equal to M by 2 ceiling value minus 1. M is equal to 3, that's why I got here 3. Right? When we are talking about the ceiling value, then 3 by 2 is equal to 1 point something. Then we can write it ceiling value, because of ceiling value we can write it 2. The 2 minus 1 is equal to 1. It means minimum number of keys will be 1 and maximum number of keys you can have 2 for that problem. And this I have explained in this table. Same thing. You can see here. And what do you mean by this M? This M is maximum children possible. Maximum number of children possible, that I told you in earlier slide, in previous slide. Right? Now, next is degree. In the next slide, we will see. If degree is given in the numerical problem, suppose degree is equal to 3, then question will be changed. Order and degree both are different. In that case, how will you find the maximum number of keys and minimum number of keys? Maximum number of keys for degree 3 equal to, you can see here, 2t minus 1. T is equal to 3, that's why 2 into 3 minus 1, which is equal to 5. Right? In that problem, you can have 5 maximum number of keys. Next is minimum number of keys for degree 3. Is equal to t minus 1. You can see here. Right? It means you can have minimum number of keys 4. Right? For degree. It means both are different. And in previous slide, I told you one example like this. Suppose here B and there is one left child and one child is on right side, that is D. Right? This pointer will store the address of this left child and this pointer will store the address of this right child. This pointer will store the address of this left child and this pointer will store the address of this right child. In this case, we can have, suppose if this is not a non-leaf node. In that case, lower bound is 2. Means t is greater than equal to 2. That is called the minimum degree. Means in the lower bound, you will always have a minimum value, that is t greater than equal to 2. That's why we call it minimum degree. Right? Because at least 2 child will be there. Right? This is for the lower bound. And if we talk about the order, that is the upper bound. Because we are saying that maximum number of children possible here. Maximum number of children is M. So this is the upper bound. Right? And in lower bound, t greater than equal to 2, which is called minimum degree. Remember this always, otherwise your question will be wrong. Right? Now we will see the operations on B3. In the previous slide, I told you how to find the maximum number of keys and minimum number of keys when order is given. And when degree is given, then how will you find the maximum number of keys and minimum number of keys? After this, we will know the operations on B3. There are basically 3 operations: searching, insertion and deletion. And one more operation is there, that is the creation of B3. Now we will see one by one. Today we will discuss only the first one, that is the searching operation. Suppose you have example this. In this example, you can see that you have to search the element 59. Then how will you start this? We will start this from the root node. And you can see here that root node has a value 45. Right? And this 45 is less than this 59. We have to search 59. Right? And this 45 is less than 59. So, we will traverse in the right subtree. Means we will search on the right hand side. Now, we will go here. 49 is also less than 59. So, then we will check or we will search or traverse on the right hand side. In the right hand side, we will see this 54, 59 and 61. Means we will traverse in this location. Right? And then you can find this 59. Because we already know that 59 is greater than 49 and less than 63. Then we will search for this element here. Right? And this searching operations can be done. And it always take big O log n time to execute according to the height of tree. Now see one more example. Suppose you have to search this 120 in this tree. We will see this root node. First of all, we will start from the root node for the searching operations. You can see that this root node is less than the searching element. Your searching element is 120. So, we will traverse on the right hand side or right subtree. On the right hand side, we will see that this 130 is greater than 120. So, we will traverse on the left hand side of this 130. Right? We will go here. And now, search the element in this location. And you can see this is the 120. These are the step by step I have written here. First search will be start from the root node. You can see on the step 1, and in step 2, it will check in which range the key is. Means 120 is greater than 100. So, we will search on the right hand side. Means control will jump to this node. And less than 130. So, it has to be in the left branch of the B tree. This is the left branch of B tree. And finally, last step 3, the control will jump to this node, and now we will get the key which have the value 120. This is the final step, and this is the algorithm. You can see here the same as I told you in the example. I have written the algorithm in a proper way here. Now the next is insertion operation. Insertion operation we will understand in the next lecture. But before that, I want to tell you that we will have the problem of inserting a new element in the B tree in university exam. So most important is to understand the how to insert a new element in a V tree. On this topic, we will have an example in the next lecture. Thank you everyone.